Everyone. We have about 30 minutes. I'm going to cover Feature Store more from the operational perspective and how Feature Store really make simplify the operationalized machine learning pipelines. I hope I'll get some time to also show you a demo. And so let's start rolling. Before we dive into the solution, so let me move things around. Before we dive into the solution and what really Feature Store is doing and how it's doing it, let's try and figure out the problem. So today, in most organization, data science started as a research practice. You get a lot of data, you analyze it, you generate reports, you send them to the business, and so on. Where in many sort of cloud native organization, Google, Facebook, etc., Spotify, machine learning is really fueling the business application. Business applications are built around machine learning. And that means that it's not enough to just like analyze, build reports, build models that are doing batch inferencing. You actually need to integrate the machine learning into an operational pipeline, which means essentially feeding data from real sources, your data warehouses, your operational Oracle or cloud databases, streaming data, notification coming from APIs, weblogs, and so on. All that need to feed into a system. The system needs to crunch it and create the features in sort of near real time. And those features are feeding the training. It's not enough to just have someone manually extract data and build some training. You want to retrain frequently to keep the model up to date. And then you build models. Those models need to be serving real applications and real data that's coming live. So in many cases, also interacting with sort of an online storage, like a key value or in-memory database. And the data from the application itself needs to essentially go back into building new features and retraining and building historical perspective and so on. So usually those pipelines that are done on the right are re-engineered. No one is essentially taking the Jupyter notebooks that the data scientist builds as part of a research or with some nice sort of click-based machine learning application. People really need to build those pipelines. In many cases, they're recoding them into Java, Scala, C code, etc. This possesses a lot of operational overhead of recoding and redoing and a lot of engineering. So we're trying to see how we can solve that problem. So when you operationalize machine learning, you see the main challenges that we've identified from customers are one, that people work in silos. You have the data scientists working in their Jupyter notebooks or IDEs, and you have the data engineers using Spark, Scala, Hadoop, and so on. You have a machine learning engineer, DevOps working in containers, Kubernetes, etc. And so how do you bridge those gaps? You don't want to move things around between the environments. You want to have one environment where everyone can work and develop and continuously put things into production. The second challenge that we see, it's a very long process to move things from development to production. Unit testing, packaging, containers, security, tuning for performance, tuning for scalability, creating CI/CD pipeline, and so on. These are practices that are usually not data science practices. Data scientists are scientists, they're mathematicians, they're not DevOps people, and so on. We need to see how to shorten that process. Another major problem that sort of is associated with Feature Store is access to features. So someone wants to train a model, it contacts the different departments, and you get a piece of CSV from here and there, and you're getting the data and you can do some training, okay? But at a certain point, you're trying to move to production, and you have to exactly the same identical features with the same statistics, with the same behavior and everything used in the production pipelines. And there, it's not like gathering data around from people through favors, etc. You have to really build those features in an online fashion, and that is a major issue. Sometimes it's politics, sometimes it's security-related issues, engineering issues, and so on. And one of the last challenges that we've also encountered a lot is that people build models. Those models are accurate in the development phase, in the training. But as you put those models into real world data, real world behaviors, their accuracy collapses. And that's because, again, they're training on certain types of data, and then in reality, the data behavior is different. Obviously, the model, which is essentially just an equation, wouldn't behave well if you give it different parameters. So this is another thing that we need to track and remediate. When we identify accuracy problems, we want to be able to, rebuild the model, build ensembles, all sorts of mitigation technologies to address the accuracy challenges. So, again, if you're looking into what is the flow in a research environment, how do data scientists work and develop? Someone is essentially extracting data, putting it in a data lake, an S3 bucket, a data warehouse. Then you take a notebook, you load data, you do all sorts of manipulations and preparations, beyond the traditional analytics of grouping and joining, but also things that relate to data science, data processing, like one-hot encoding and grouping of values and date mappings and so on, to turn data into something that's machine understandable. And then once you build the data, you want to train it using either a black box tools for AutoML, some of the cloud services, DataRobot, etc., or using some, again, notebooks that you feed the data in, you run some, sklearn or TensorFlow, etc. You build a model, and then you evaluate the model using different testing methodologies. So this is the practice where people develop models today in an interactive fashion. And then you say, you know what, let's just go and build that model into production. We have a model, let's put it behind some HTTP endpoint, and we're done. This is where they're going to get some shock treatment, because putting an application into production is way more complicated than just putting a container behind an HTTP endpoint. These are the things that you need to build into a production application. So even this small thing of building models have to be done in sort of a more automated way, that every time we extract new data, we want to retrain as an automated pipeline. So we need to take the code that was done in Jupyter, turn it into containers, and we may want to add other steps here. Maybe the training need to work on scale, on like 100 gig worth of data, and not like 1 gig of data that we used in notebooks. Maybe we build models, they're not good enough. We want to further optimize. We want to do hyperparameter optimizations, compression techniques, etc., for the models. And finally, we want to automatically deploy the models. And we need to store all the information, the models in the repository, the experiments in repository, etc. But this is just one piece of the puzzle. When we build the models in the production pipeline, it's not enough to just put an HTTP endpoint behind the model. Something needs to build the features in the production pipeline, essentially in real time. So we need to build a complete pipeline in the operational aspect, where it essentially listens on an HTTP endpoint or a stream endpoint like Kafka. It takes the JSON, it parses it, it enriches the data with data from the some other storage, builds the feature vectors, contrast the feature vector with the model, take the response, do something with it, send it to a message queue, respond to a user with some nice and handy response. So there's a lot of work there. But again, many other pieces, like you need to do model monitoring. You need to collect all the data from the training, from the serving, be able to compare those to see if the data is accurate, if we have accuracy problems. But really the biggest challenge is building the data, which is all the data engineering and feature engineering work that we did in small scale. We want to build now, tapping into production data sources, whether these are data warehouses or online databases or streaming technologies or HTTP endpoints and so on. This may also require glue logic and containers and working with technologies like Spark and Flink and so on. So this is a very tough problem. And one of the biggest challenges is that these are unsynchronized sort of efforts. So let's assume I built a new model, and that new model requires new features. So essentially I have to redo my feature engineering pipeline, because again, if my new model requires few new features, the old feature engineering pipeline won't work. So we need to see how all those efforts are coordinated, how we essentially apply versioning across all those different components in the stack, and how we deliver that faster. So this is essentially what we're trying to do in Iguazio, and we're building a bunch of open source frameworks that are trying to automate all that mess using various orchestration techniques with serverless technologies and so on. So essentially what Amirun, which is the open source framework that we've contributed and working on, it has 4 different pieces into it. So it's a more holistic view of operational pipeline. It's not just a feature store like in some other solutions. Essentially, you have 4 main parts that are very well integrated between them. So which means that you can version everything as one thing. You can automate the flow of data and metadata across them without writing any glue logic and so on. So the first piece is the online and offline feature store, which we're going to zoom in a minute. Once we build the features are generated in a way that there's a sort of an offline option to get the features and an online real-time way of getting features. The offline features are going into sort of a CI/CD pipelines for machine learning based on various technologies, Kubeflow, GitHub Actions, etc. But this allows us to essentially build the training model of the feature store and do validation and testing. And also we need to extract additional data from the models that will be used for other automation. We'll look into that, like extracting statistics from the data, extracting information about the model, which will be used later on in the process for comparing the model behavior with the expected behavior for identifying accuracy problems, drift, anomalies, and so on. So this is the first part. The second part is once we generate the model and we have the online data, we want to build a pipeline of inferencing, which is not just the model serving part. It also contains the parts about API integration, the front-end integration, taking the JSON and parsing it, and potentially data preparation and enrichment using the capabilities of a feature store. And finally, serving one or even multiple models in sort of an ensemble and doing some post-processing. All of that is built into a pipeline, which is very automated. We're going to see that in the demo. And that model serving part keeps emitting information. The information is the request of the user, the response we gave, etc. That information that we emit from the serving pipeline is essentially built again as features into the feature store. So if we want to retrain our models with fresh data, we don't need to recollect the data. The data is already there. It's essentially new versions of the same feature sets that could just feed a new pipeline that gets triggered on an accuracy problem or user activity or a changing code or changing data. And again, everything flows as one continuous operation pipeline for the different pieces of data generation and feature engineering, sort of building the models, real-time pipelines, and the model monitoring. And that integrates very well with the rest of the ecosystem. For example, the training can be done using the Amirun built-in serverless functions for training, but could also use any other AutoML framework, but just invoking that, whether it's Azure ML or SageMaker or DataRobot or H2O and so on. The data in the feature store could be accessed using JDBC or Pandas or other tools for exploration. Again, there are integrations with Notebook, including native plugins for Jupyter for doing all sorts of cool stuff like converting notebooks to managed services. Again, and all those different pieces that you see here, there's essentially a glueless integration with all of them. The result is essentially operationalizing machine learning 12 times faster. We have a bunch of use cases and case studies showing how organizations build complete operational pipelines in less than a month by applying all this automation and abstraction. And essentially, instead of thinking of a research and then saying, you know what, let's deal with operations later, thinking first about how you build operational pipeline, and then going backwards, what needs to be built into that and how to integrate with the research and development environment. So if we're thinking about how things are done today, essentially you develop something in code, then someone, whether it's a DevOps guy or if you're a skilled developer, you build everything as containers and Kubernetes artifacts, deployment spot, all of that stuff. Then someone needs to take all of those things and and build a pipeline, which involves the feature engineering, a pipeline of multiple stages of multiple applications, training, testing, feature engineering, and so on. Once you build all of that, someone else goes and build all the instrumentation, logging, monitoring, telemetry for those deployments. And that telemetry is usually not really connected to the application. So you manage and you collect information about CPUs and GPUs and memory and application logs and so on, but that's not really what you want to monitor. You want to monitor an SLA of an application, you want to monitor behavior of a model, etc. So the process that we've taken with Emerald is essentially through automation and serverless technologies. You take code, you essentially have one command line or one SDK call that will take your code, whether it's part of an IDE like PyCharm or part of a Jupyter notebook, will automatically turn into a managed elastic microservice, okay, like a serverless function. And that thing would actually auto scale. So if you have challenges around scaling out a computation, that's taken care of automatically. And it actually supports different engines as an underlying technology, including things like Spark and Dask and Horvath for deep learning tasks and sort of Nucleo for real-time tasks and so on. So it knows how to create the most optimal processing engine for the workload that you have, which also leads to much higher performance overall. It optimizes the performance of your application, whether again, it's a feature engineering application or a model serving application. And the next thing is essentially once you compose those functions, think of them as Lego bricks or building blocks that you could just go in and put them in a pipeline and just say pipeline run or get the pipeline to trigger on some activity and so on. And all the telemetry, whether it's managing the models, monitoring the models, monitoring the experiments, monitoring the jobs, monitoring the GPUs, everything is automatically instrumented as part of those serverless functions. You don't need to add anything. You essentially add potentially an import or an SDK line to your code, and that's it. It all gets tracked automatically. We won't have time to cover all that, but I'll show you some of it as part of the demo that I'll have. So again, the four pieces that are built into MLrun is one is the feature store, which supports online and offline functionality, including the automated feature transformation. Some feature stores focus on cataloging features, but generating the features is done elsewhere. In this feature store, it leverages the serverless engines to essentially build the features in an automated way, whether it's real-time from streaming data or offline from batch data. Then again, you have the other pieces that I mentioned, the automation for building the models, the real-time serving pipelines, and the model monitoring and retraining facilities. So you have a complete operational pipeline. Let's zoom into the feature store, and again, then we'll see a demo. So essentially, the feature store has two parts to it. Essentially, one part is feeding the data, is generating the features. The other part is serving the generated features and joining them, time scaling them, etc., and providing them to the different applications. So again, the first part is connecting two different data sources. What is a data source? Could be an S3 bucket with some Parquet file. Could be a Kafka stream or a Kinesis stream or RabbitMQ stream. Could be an HTTP endpoint where someone is feeding features at you. So it supports real-time scenarios and batch scenarios. Once the features are in the feature store, you can just go and do exploration and work with it as a Pandas data frame or as a Spark data frame or various other formats, through JDBC and Presto, access it through traditional exploration tools. You can access it directly from notebooks using the SDK. And when you want to do training, one of the things that when you train on production data, think of it, I'm having features being generated all the time for the next 5 years. I'm not going to train data on everything, especially if I want to retrain models. Essentially, what I need to do is to create a snapshot from the production data, which sort of windows take a time portion of the infinite time, and builds a snapshot, a Parquet file, for example, from all that data, which could be transient and in memory and so on. I want to build some materials view in like a Parquet file, throw it into a training system, run the training, and return the results. By the way, there is also a return path because the training data feeds back the feature store with information that will be used later for things like imputing and model monitoring, etc. So this is sort of the offline part. The online part is where essentially the model serving can just do a get on a feature vector, and within milliseconds, it will get back a response with the full feature vector. And again, the model monitoring will write back. So it has on one leg, which is reading metadata from the feature store in order to do things like comparisons and accuracy measurement, etc., but also writes all the production features back into the feature store for reuse in later application. So what's the benefit of using such an architecture? First, it's a very fast, simple, scalable way to build production features. So not manual, SQL operations and so on, but something that you can produce features. It's always on, 24/7. It's very scalable, supports real time, offline, etc. So it's very production oriented. The other nice thing is I'm going to show you in a minute. You don't implement features twice. You implement features once for online and offline scenarios. So I can implement the features, essentially build analytical pipeline for creating a feature once, and then I could feed that feature from a file, from a stream, and I could decide that this engineering pipeline creates a training set or creates an online feature. So in most cases today, there's a separation. The offline features, the batch features are using technologies like SQL, etc., to build those features. For online features, you're using stream processing, like Flink and Kafka and all that. That's essentially different languages, different practices, a lot of headache for people that need to rebuild it and redesign it in the new way. So in this mechanism, it's a very abstract logic. We'll show you you build high-level Python classes that builds a high-performance, scalable analytical pipeline for you. Once you build those features, they're cataloged with a lot of metadata. So someone can just say, you know what, I need those. I'm building, credit application, but maybe I want to predict lifetime value of a customer. I just need five more features and 10 other features that someone else built, and I could just build a new application from this catalog, or I can even share across teams. Maybe a data scientist builds a feature, builds it as a scratch, simple, naive implementation, but then a data engineer says, you know what, but your feature is not really designed for scale. You didn't think about your validation policies and error handling and maybe security issues. You can go and take the same features and re-implement it with a new tag called production, okay? And then use that in production versus the development thing that the data scientist did. So it allows collaboration across teams and across projects. This architecture also is glueless. So if I want to do model monitoring, it just feeds off the feature store, and we're going to see that in a second. And also we can retrain directly from production data because, again, sort of a single source of truth for everything. Now, some of the practices that have been there for a while for building features are using SQL. So why not use SQL for building features? This is just an example I grabbed from the internet for building a feature with some time aggregation, etc. You see a nested select statement. So that's huge amount of computation. It's very complicated to build and do something with it. Very resource intensive, and that thing will never run in real time. So you cannot take this thing and throw a Kafka stream at it. It just won't work. Okay, so we need a different approach to building features, something that's higher level abstraction, something that runs in real time and or batch. So we have a different approach to that. So essentially what we want the data scientist or data engineer to do is use the native tools that he's familiar with, whether it's native pandas or Python classes, whether it's PySpark, if he wants to build very high-level logic, and then that high-level logic will translate itself automatically into a distributed serverless architecture. Essentially, those things will get mapped into containers and serverless function and SDKs which know how to auto scale. And again, we can support different engines, whether it's Nucleo or Dask or Spark or other engines. Those those feature analytics, pipelines are going to manipulate the features and throw the results into a unified online and offline store, meaning the same thing will map into like offline or online data. And then we can use it in different forms, again, materialized view for serving, for training, and for monitoring. When we're building the features for real time, again, there are a lot of other issues. We need to think about performance and robust transformations that won't fail, while systems are up and running, consistency of the data between training and serving, data drift, all of those things that are listed here. Again, it's a huge effort, and essentially we can, instead of doing all of that, think about just building this pipeline, which is actually used for one of the demos. I won't go through the entire demo. I'll share with you the link because we don't have a lot of time. So essentially, this pipeline is the complete pipeline for a fraud application. This is all the code that you need to do. That's it. No SQL statements, etc. We build a pipeline. The pipeline has sort of date mappings and mapping values, categories of age, and doing one-hot encoding, and then building aggregates across different columns of the original data and so on. And it could go on and on and on, but you can build essentially very complex pipelines in like a couple of dozen lines of code in Python. And those will go into the feature store, and you can also create versions, everything is versioned. And this process could be launched on a Kafka stream or on a batch job. So as a data scientist, I can just go develop the features with a CSV file in my notebook. If I feel everything is great, I'll just deploy it into production, listening on a Kafka or an HTTP endpoint, or in a scheduled job that reads from S3 bucket or whatever. So that's generating the features. Once we generated the features, they all go into a catalog. So I could just go and pick and choose features and build a feature vector. Then I could use that feature vector for offline, for training, or for online, for serving. And finally, the monitoring works with the same data. So what is sort of accuracy monitoring or drift monitoring? Essentially comparing the production data behavior, statistics, standard deviation, histograms, and so on, with the training data statistics, okay? So what's the best place to store statistics of a feature if not a feature store? So the feature store all the data from the training, etc., in the feature store with all the statistical metadata of every feature. And the model monitoring calculates the real-time statistics of every feature. And essentially compares the two to figure out that there is a drift, or even do a deep dive, zoom into feature behavior in production, because everything is working around the same thing. So one of the key demo applications that we have is the fraud prediction demo, which shows the full flow of everything I just spoke about. So on one end, it has the ingestion pipelines. The ingestion pipelines are using the real-time Nucleo serverless engine. It's also an open source project from Iguazio, very, very popular, more than 4,000 stars in GitHub, used by many of the cloud providers. So this engine essentially knows how to tap into things like Kafka, HTTP, Kinesis, and about 13 other protocols. It knows how to auto-scale, checkpoint, deal with all the big issues of production deployments, and you just give it a piece of code and it generates all the managed service around it with monitoring, logging, and so on. So essentially what the feature store is doing is using those Nucleo serverless engines and deploying the business logic of the analytic pipeline into them. The feature store, as we mentioned, also supports things like Spark and Dask and others. So things that are more batch, maybe Spark is actually a better tool for running batch ingestion from some data warehouse. So it actually supports different types of data, the transactions, swipe transactions, the account activity logs, which are real time, and some static data, which is batch ingested. Everything goes into the feature store, and you can just explore that using a Jupyter Notebook. Then when you want to build the training model, then you use the combination of Emerun and Kubeflow. Emerun knows how to orchestrate Kubeflow as a pipeline engine, as well as other pipeline engines like GitHub Actions or GitLab CI if you want to. So essentially, you can just go and build a CI pipeline that will do things like feature optimizations, selecting the most optimal features, drive the result into an AutoML serverless function. Then you have another function that deploys and tests the model in production, verify that the model is deployed, working properly, etc. Once it's deployed, then those serverless functions, the real-time serverless function, are creating API endpoints that can listen on the actual data coming from Kafka, enrich it with data from the feature store, and respond to the user. But also the model monitoring part will tap on the serving engines and rewrite the data into the
left.
Okay, so we don't have a lot of time, so the only thing I'll do is I want to show you where this demo exists. Go out of the sorry.
You're busy at work, I see.
Yeah, I am very busy at work. Just open a new window. Sorry. Okay, so Emerun has its own landing site, and this landing site has the documentation. It also has the function marketplace. So a lot of things are built in. And if you scroll down into the feature store, there is feature store end-to-end demo, where what you'll see is the demo that I mentioned. It contains 3 notebooks that could be downloaded, and those 3 notebooks have the part about building the features for the fraud demo. The second notebook is showing how to essentially build a feature vector and take the feature vector and do AutoML, including feature optimization, like automated feature selection. And the third demo is the serving pipeline that essentially shows how you build a complex ensemble, a few lines of code building complex ensemble with automated feature enrichment. So essentially, you don't need to do anything around the feature store. You just need to give the ensemble the URL of the feature vector, imputing policy. Part of the issue with real-time features, in many cases, they'll get nulls and non-values and things like that. So you can essentially tell the real-time pipelines to substitute null values with statistical values taken from the feature store. So again, all that is done in like just few lines of code. You can test your model, your behavior of your machine learning pipeline in a notebook. And in order to put it into production, you just say deploy. That's it. And you could see all those notebooks in the website. And feel free to contact me through LinkedIn or any other media. Happy to address any questions.